Good evening, sir. My name is Aaron Tony Anak Sedunggau. My metric number is 05 DKM 23 F1106. My partner is Muhammad Nur Rashid bin Muhammad Zakaria. His metric number is 05 DKM 23 F1021. So our presentation will be about understanding defect and distortion in welding.
For our list of contents, first one we have introduction, second understanding welding defect and distortion, third one is case studies and real life example, fourth one is strategies for mitigation and quality improvement, last one is conclusion. For our introduction, the welding process is intricate and requires a deep understanding of potential defect and distortion that can occur. This presentation focuses on recognizing, analyzing, and effectively managing defect and distortion in welding, aligning with the need of continuous learning and independent updating of technical knowledge at an effective level.
So for the next slide is understanding welding defect and distortion. Common welding defect. The first one is porosity, the presence of small cavities or void in the weld metal. It often appears as a cluster of small gas pockets. The causes is contaminated base metal or filler material, improper shielding gas or inadequate gas flow. So to prevent this to happen is use clean base metal and filler material and use proper gas shielding. The impact on the structural integrity is reduced material stretch and strength and can act as stress concentration point. Next is compromise the corrosion resistance of the weld. To detect this situation is visual inspection where the porosity appears as small round and elongated voids. Non-destructive testing method like ultrasonic testing can identify surface porosity.
Next is lack of fusion. It occurs when the weld metal failed to fuse with the base metal or the previous weld, caused by insufficient heat input and incorrect welding technique. For the prevention, we can use optimized heat input and use proper welding technique. The impact on structure integrity is that it can reduce the load-bearing capacity of the joint and increase susceptibility to cracking and fatigue failure. For detection, we can use visual inspection as it may reveal incomplete fusion as a visible line or gap. And last one is ultrasonic and radiographic testing can identify lack of fusion in critical areas.
Crack. It can be longitudinal, transverse, or crater crack and may occur in the weld metal or heat affected zone. The causes is rapid cooling and high residual stress. To prevent this is we need to control cooling rate. We need to reduce residual stress through the proper preheating and post-weld heat treatment. The impact on structure integrity is initiate stress concentration point, reducing the material load bearing capacity, propagates under cyclic loading leading to the catastrophic failure. Detection visual we need visual detection for visible crack and dye penetrate testing for surface crack.
Distortion, longitudinal shrinkage, caused by high heat input, which is rapid cooling lead to longitudinal constriction. Next one is inadequate fracturing, insufficient support for the weld component, impact on the structure integrity, introduce tensile stress, reducing joint strength. Detection, we can use measurement of distortion using precision instrument. Next one is transverse shrinkage, caused by uneven heat distribution, which is unequal cooling rate. Next one is poor joint fit-up, misalignment of joint component, can also cause of transverse shrinkage. Next one is impact structure integrity, can induce bending stresses in the joint. For the detection, we can use visual inspection for misalignment, measurement of transverse construction.
For the next slide is case study and real life example. Project description. A construction project involved the fabrication of large structural structural steel frame for a commercial building. The process used was a gas metal arc welding (GMAW) welding defect encounter. During the inspection phase, several welding defects were identified, including porosity, lack of fusion, and incomplete penetration. This defect compromised the structural integrity of the well and raised the concern about the project safety. Lesson learned from the situation is the welder involved in the project lacked proper training and certification for the scientific welder a welding process use. It was discovered that ongoing training and certification programs were essential to ensure that the welder were up to date industry standard.
Next one is Inadequate Welding Procedure Specification (WPS). The initial WPS did not adequately address the requirement for the project, leading to improper welding parameters and techniques. It was crucial to develop and adhere to comprehensive WPS tailored to the project specification. Measures taken to rectify issues. Welder training and certification. The project team organized additional training sessions for the welder, focusing on the specific welding process and techniques required for the structural steel fabrication. Welders were also required to undergo certification to ensure competency. Next one is enhanced quality control and inspection. The project implemented a more rigorous quality control and inspection process, including non-destructive testing methods like ultrasonic testing and X-ray inspection. This helped identify and address defects at an early stages. Last but not least is continuous learning emphasis. The project highlighted the importance of continuous learning and adaptation to evolving industry standards. Regular training programs, updated welding procedure, and enhanced quality control measures become integral component of future projects. For next point is strategies for mitigation and quality improvement, which is advanced welding technique. First one is laser beam welding, also known as LBW. It uses a focused laser beam to melt and join metals. This technique offers precise control over the heat input, reducing the likelihood of distortion. It commonly used for welding thin material. Next one is electron beam welding, also known as EBW. It employs a focused beam of high-velocity electron for welding. This technique produces narrow and deep weld with minimal heat-affected zone, reducing distortion and defect. Pre-welding preparation. First is material selection and preparation. Choosing material with compatible properties and ensuring proper cleaning and prepping of surface help prevent contamination and reduce the risk of defect. Second one is joint design. Optimal joint design, including bevel angles and gap tolerance, can significantly influence the welding process. Proper joint preparation promotes better fusion and reduces the likelihood of defect.
Post-welding treatment, heat treatment. Controlled heat treatment process can relieve residual stress and reduce distortion. Post-weld heat treatment is particularly effective for certain material and application. Next is surface finishing. Proper surface finishing techniques such as grinding or machining can eliminate defect and improve the overall appearance and integrity of the weld. Next is continuous learning and innovative approach. The first one is training and certification. Continuous training and certification program keeps welder update on the latest technique and technologies fostering a culture of continuous improvement. Next is collaboration and knowledge sharing. Networking with industry peers participating in knowledge sharing forum facilitate the exchange of best practice and innovative solutions.
In conclusion, welding defect and distortion are inherent challenges in the welding process, but strategic measures can effectively mitigate their impact. Through pre-welding preparation, post-welding treatment, and continuous learning, embracing innovative approach and implementing robust quality control measures further ensure the consistent improvement of welding process, ultimately enhancing the overall quality and integrity of welding structure. That is all from us. Thank you.